Hey guys, welcome back. So today we're going to be talking about symmetry, which is one of the easier topics of this chapter, but there's some tricks here and there that still need to be covered. So let's get started. Here we go. So whenever we talk about symmetry, we would like to think about the most generic way of symmetry that we've been taught for a while, which is looking at a line and looking to the left and to the right of that line and seeing if it's the same or not. For example, there's a little flower here. To the left or to the right of it, we base symmetry looking at the picture, is the same or not. So here we say that it is the same, so we give it a check mark, it's good. We look at the other figure, this flower isn't asymmetric, so we're going to say it's not the same on both sides of this line, so we say it's not symmetric. So, however, in calculus, there's two types of symmetry that I like to focus on. The first one is the one we have been talking about, which is y-axis symmetry. And the second one is going to be called origin symmetry. Origin symmetry is something that we have not seen as much, but let's check it out. So first we're going to discuss y-axis symmetry, which is the one that you guys have seen previously, hopefully, or you may have not. However, in calculus, we call these functions with y-axis symmetry even functions. So they're called even functions. So whenever you hear that a function is even, what they're referring to is actually their symmetry. So let's see how we can find a little trick here so we can actually calculate if a function has y-axis symmetry without having a picture of it or the graph, just by having the formula. So here we have a little box here that says f of negative x is equal to f of x. What exactly is that, right? So we have f of negative x and f of x. Let's just look at their inputs, right, which is f of negative x and f of x. Let's draw it out. So we have a negative x and we have an x, right? So looking at that, let's just say that they have a y value that is exactly the same. Okay, their f of x's are the same, so they're talking to their y values. So we're gonna start here at f of x, and it's gonna have a y value which we're gonna call f of x, right? But it says that f of x has to be equal to f of negative x. So that means that f of negative x's y value is gonna be up here, right? And it's going to be exactly the same as f of x's. So since they match, since their y values are the same, although you're opposite sides of the x, that means that you have y-axis symmetry. So let's draw a function that fits through here, and a very easy function to think about, I would say, is an absolute value function. Alright? So an absolute value actually has y-axis symmetry, and therefore we say that an absolute value function is an even function. Alright? So let's look at an example so we can see how we can apply this, right? So we can use the formula to check if f of x is equal to f of negative x, right? So we already have this part. We already have f of x. So now we need to compute the other part, right? We need to compute f of negative x. So we're going to do that. We're going to have f of negative x here. So we're going to have negative x squared minus 1. Then we're going to keep solving it. Negative x squared is just x squared minus 1. So we check. Is f of negative x equal to f of x? So we look over here. F of x is equal to x squared minus 1. And f of negative x is equal to x squared minus 1. Since this checks, this means that we have y-axis symmetry. So this is what we did without having a graph, right? But let's look at the graph so we can actually connect what we have here to a visual function. So what this is, x squared minus 1, it is just a parabola shifted 1 down. So this is what we have, and what we're testing is if we draw a line on the y-axis is the same to the left or to the right of that line. So here we look at it and yes, it is the same. But we didn't need this graph. We no longer need graphs to look at symmetry. Now we can just look at the function, apply a little formula in the box, and then check if it has y-axis symmetry or not. Alright? So now let's look at another type of symmetry, which we're going to call origin symmetry, which is the second type of symmetry that we focus in calculus. So functions with origin symmetry are called odd functions. So let's put that in there. It's called an odd function. Alright? So whenever we have a function that has origin symmetry, we're going to call it an odd function. Now, let's see how we can look at this odd function and we can test if it has origin symmetry. Right? So once again, we're going to have a negative x and an x. Right? So we're going to have a negative x here and an x. So now we're going to say that f of negative x, so let's get this value of f of negative x up here again, right? It's going to be equal to, this right here is f of negative x, right? It's going to be equal to the negative of f of x. So normally, f of x was up here, right? As we had it before, but now it's not going to be there. It's going to be on the negative side. So instead of being here, it's going to be directly reflected over the x-axis, so over here, right? So you're going to go from f of x up here to f of negative x down here. Negative f of x down there. So it's going to be the same length here, but just down. The opposite direction, right? So now what we're going to say is that if there's points on the graph that look like this, one is going to be on f of x and the other one's going to be right here opposite at f of negative x, then that means that these functions have origin symmetry, or they're an odd function. So another way to look at this actually is to reflect it over the origin or the y equal to x line. We see that they're exactly opposite and they're reflected over this line. They're reflected over the origin, right? So a function that we can think about that has origin symmetry that will fit through here will be something like a sine graph. A sine graph is actually a very common example of a function that has origin symmetry. Now the hard part is going to be for me to make it fit through those lines, right? So I'm going to actually just try my best here. Let's try to work with me there. So if you guys see, I have tried to draw a sine function. So we said that a sine function has origin symmetry or is an odd function. So now let's test if this function here that we have, an x cubed plus 1, has origin symmetry. So once again, we're already given, actually we're not given f of x. We're given f of x, but in their formula we don't care about it. We care about f of negative x. So we're going to start off with that. We're going to compute negative f of x, right, by applying a negative to this whole function that we have here, right? So what we care about is we apply a negative, so it becomes negative x cubed minus 1. What we did there was just distribute this negative into here, distribute this negative into here, and it gives us that. So now we're going to check if this right here, right, is equal to f of negative x. So now the second thing we're going to compute is f of negative x. So we're going to input negative x into x cubed plus 1. That gives us negative x cubed plus 1. So now, is this equal to this? And we say it is not, so we do not have origin symmetry, therefore this function is not odd. So once again, let's look at a graph of this function and see what this looks like. So if you remember from our library of functions, this right here is a cubic function shifted 1 up, which looks like this, right? So the fact that I shifted it 1 up, it makes it lose its origin symmetry, because if I were to shift it, if I were to have it at its original point, just down here, right, it would have that origin symmetry. But since we shifted it up, we lost that origin symmetry. So in case you guys were thinking that this is called an odd function because it has an odd exponent, that's a wrong assumption to make. You should always check and not just assume because it has an odd exponent that it's going to be an odd function, right? Because for the first one, if we go up here, right, we have an even exponent, and then we say that this function is even. So let's not make those assumptions where because of the exponent we say the function is even or odd. It is actually because you need to test it and see what happens. Alright? So now we're going to talk about the last type of symmetry, which is the x-axis symmetry, right? So it's going to be y-axis symmetry, origin symmetry, and x-axis symmetry. So functions do or do not have x-axis symmetry. So let's think about this, right? So I'm actually going to tell you that functions they don't have axis symmetry, and I'll tell you why. Let's look at the graph right here on the right. This graph in blue that we have here on the right. This right here is an example of something that would have x-axis symmetry, right? So what we say about x-axis symmetry is that we look at the x-axis, right? I'm going to draw right here. I'm going to draw this dashed line here in red, and then we look on top of the red line and under the red line. So we obviously see that the top is equivalent to the bottom, so we do have symmetry. However, why do functions not have x-axis symmetry? So let's look at our second bullet point, and here we have that the graph fails the blank test. So if you guys remember, functions need to pass a certain test. Is it the vertical line test or the horizontal line test? Yeah, it is the vertical line test, right? So since we test the vertical line test on this function, right, we obviously see that it fails it because it touches the vertical lines more than once, and it also does over here, right? So since a graph, not a function, since a graph with x-axis symmetry fails the vertical line test, we say that functions do not have x-axis symmetry. So now the equation, this graph that we have here is very common, and its equation is x equal to y squared. Alright? So you should always look out for x equal to y squared, because anything that's a y squared or y to an even power is not gonna be a function, because it's very likely to have x-axis symmetry. Doesn't always have x-axis symmetry, but whenever you have y squared or y to an even power, you should look out for them, because they're more likely to not be a function and have x-axis symmetry. So that's about it for now, but there are some more variations of symmetry and other functions and how it's applied, so check out the practice problems, and see you next time.